So now we have to check the direction of the current, whether it is incoming or whether it is outgoing. If it is dot, the opposite also should have dot. But whereas here we are having a cross symbol. So we are just zooming it. So it is a cross symbol and it is a dot. So now again, here it is cross and here it is dot. So this is mismatching. So we have to recorrect this one as dot and this one as cross. So this comes under coil 3. So now, so this has to be, coil direction should be reversed, so it is cross, and this one has to be reversed, the coil has to become as dot. So phase A gets over. So now we are concentrating on phase B now. It is dot, cross, and then here it is cross, and then dot. So this one also should be get changed. So this one comes under coil 1. So here it is, I just double click it so that the coil direction can be reversed. So it is dot and here also it is dot. Here it is cross and here also it is cross. So dot indicates the incoming current and cross indicates the outgoing current. So here it is dot, here also is dot, cross and then cross. So this one is current. So now we have to give any one of the phases with an ampere of current. So for which phase we have to give? So according to the principle, so this is the unaligned condition. So with this unaligned condition, we have to excite the machine. So for coil 3, I just give the excitation as current to be as 1 amps, and then I have to give a boundary condition. So initiate as 0, 0 and initiate as 0, 55. So draw a outer line after the back end of the stator and then make it as air region. So we have to select this ignore poles so that there will be no poles found here. So all this region will be indicated as the air region. So here I just selected the material to be as copper, so replace to air, so that everything becomes an air. So now go to the tool and then go to the view and then get initiate to the mesh. So now the mesh size is bigger. The mesh size is bigger, so it won't give an accurate result. So for this reason, we have to go for meshing. So select the mesh element size as 1 mm and then mesh it so that the mesh size will be very, very small. So this gives the tiny rectangular shape. So this is the rectangular shape. So it is very, very small, so that it gives the accurate result. So now just rotate the value. So solve and then go for a static 2D. So now we have obtained the result as 0.2325 What is the unit here? The unit here is Newton meter, is 0.2 Newton meter. Ohmic losses is 1.52 units. So what happens to the flux density? The flux density is go to the field and then give flux function and update the view so that we can be able to get the flux path. If you want to give an exact flux path, so select the none and update view so we can be able to get an exact flux path. If you want to get a flux density, select flux density smoothen and then update the view. So that we can be able to get 0.531948 as the flux density. So now the red color indicates the higher flux density. So where this higher flux density occurs? So this higher flux density occurs at the stator poles. So now go for the fifth view and then go for the object. That is, go for the solid model. This one has rotor. Go to the go to the magnet and then get the rotation angle and then go to the angle and here this number it is 0, 1, 2, 3, and then type up to some 20. Then go to the rotor and here we can able to see a rotation angle. So type it as percentage angle percentage degree. Then okay and then solve a static 2D. So the problem left is 20 and now it is undergoing the second problem. So the memory occupied space is 127.6 MB and maximum available to my lap is 2 GB RAM. So if you want to know what is going on here, so you mentioned as it is applying mesh and mesh boundary is smoothening. So a lot of things is happening for the electromagnetic analysis. So just so 8 problems gets over is following on the ninth one. Ninth also gets over. So it gets simulating. So now it is solving the last one. The solution is obtained. So just click over here and go for the graph selection. It just gives the 0.55 Newton meter as the torque for the entire rotation of the rotor. And then go to the update view, then just animate it. So now we can see how the rotor is rotating. So now the rotor starts to rotate. So as the rotor is rotating, you can be able to see there is a variation in this region at this values. So it indicates the number of frames it is utilized. So this is the static analysis for an switch reluctance. Thank you.